Probably nearly everyone has heard about how difficult it is to solve the three-dimensional Schrödinger equation. That's the reason we have the whole topic in math science called separation of variables. In the spherically symmetric problems, however, there are standard techniques which basically reduce the initial three-dimensional differential equation to a single-dimensional one. First of all, for those who are just vaguely familiar with the subject, the following equation is called a one-dimensional Handholds equation. Those who are familiar with the subject may skip this introduction and go immediately to the problem set. But here are the essential steps. First, consider the three-dimensional stationary Schrödinger equation. Here, m is the mass of a particle, delta is the three-dimensional Laplace operator, and u of r is the potential energy. Or one can rewrite it as a Helmholtz type equation, where k squared is a coordinate-dependent wave vector. One of the most well-known cases when this Schrödinger equation gets simplified is when the potential energy depends on the modulus of the radius vector only, a so-called spherical symmetry case. Then, we can drastically simplify the equation by introducing the spherical coordinates. The spherical coordinates are given by the following change. Here r stands for the radius, theta for polar angle, and phi for the azimuth angle. The surfaces of the constant r, theta, and phi looks as sphere, cone, and plane respectively. One can prove after a rather tedious calculation, or after a rather simple one for those who are familiar with Lamé coefficients, that Laplace operator can be rewritten as follows. Here we will concentrate on the most typical case of scattering problems, when the scattering event is independent of the azimuth angle phi. We seek for the solution in the following form. Namely, we split the solution into the radial and angular parts. Then we arrive at the following equation. The left-hand side of the equation depends on r only, while the right-hand side on the polar angle theta. Then both parts are equal to some constant. Let's denote this constant in a slightly unusual manner, nu times nu plus 1. Then we have two separated equations. The first one is for the radial part, while the second one is for angular part. Let's slightly rearrange them. Now if we make a substitute, then the term with the first derivative drops out of the radial equation, and the equation becomes a typical one-dimensional Helmholtz equation, with the radius-dependent wave vector k. In the angular equation, we may change cosine theta to x, and it is turned into the following. This is a celebrated equation in mathematical physics. It is called the Legendre differential equation. In 2 weeks' time, we'll prove the following integral representation for it, where the closed contour C is depicted in the figure. Well, there are actually two contours, which give two linear independent solutions. But I present here just one. Again, in 2 weeks' time, we'll prove that the equation has the regular at all values of theta, including z-axis where theta equal to 0 and theta equal to pi angles, solution only when nu is an integer. Armed with the counter-term trick, you may try to prove it yourself already. Therefore, if the problem requires you to seek for the solution regular in the entire 3D space, the nu must be integer, and you may classify the solutions of the radial differential equation with some integer index L. So, this is how the 3D problem is simplified and reduced to the solution of the one-dimensional equation with corresponding boundary conditions. However, sometimes the potential of the Schrödinger equation consists of two parts with different symmetry. For example, such is the spherically symmetric Coulomb potential, hydrogen atom, and the externally applied uniform electric field, axial symmetry. In this context, let's discuss some coordinates which are especially suitable and allow for the separation of variables. They are called parabolic coordinates. The name parabolic comes from the following 3D figure. The constant axis surfaces, psi is equal to constant and eta is equal to constant, are the paraboloids. You can easily compute the Laplace operator in these coordinates. Now, I don't want to spoil you the pleasure and consider the exactly solvable problem with such a potential right away. You will find it in your homework assignment. Instead, I'll show you how to separate the variables in the case of Coulomb potential with the help of parabolic coordinates. The answer is of course known. For bounded states with negative energy, we should reproduce the hydrogen atom energy levels. So here is our potential. Now we see the wave function in the form of the product of three functions, where m is an integer. Why? That's because psi of x at n phi should be phi periodic function with period 2 pi, due to the equivalence of angles phi and phi plus 2 pi. For definiteness, let us assume m to be positive. We introduce now the wave vector notation. We'll be seeking for discrete energy levels, E smaller than 0, hence E is equal to minus modulus of E. Substituting these ansatz after a simple transformation, we obtain. As a result, both parts depend on psi and eta separately, so they are both constant. Both equations lead to identical Kummer functions. Let's consider the second one, for example. Now we need to reduce it to the hypergeometric one. To this end, we seek for asymptotics for the solution at large and small eta. At large eta, we drop the term with the first derivative and retain only the second one proportional to eta in the term f2. Minding the fact that we ought to obtain a bounded solution at eta tending to infinity, we choose asymptotics with minus sign. At small values of eta, we try to seek for the solution in the power law form. f2 is proportional to e to alpha. Therefore, we keep only the first three terms in the equation. And we immediately get the correct power law asymptotics at small eta. Therefore, we form the following ansatz and arrive at the following differential equation. With a simple substitution, eta is equal to x over kappa, we reduce it to Kummer form. And the general solution is the combination of two confluent hypergeometric functions. The solution should be finite at eta tending to 0, that means a2 should be put equal to 0. The remaining Kummer function has an exponential asymptotic at x tending to infinity. As a result, the wave function blows up, unless the first argument of the hypergeometric function is a negative integer. In this case, as you remember, the solution is polynomial, and the behavior of the solution f2 of eta changes cardinally. As you see, the polynomial growth is beaten by the exponential decay. Therefore, this function is precisely what we need. The same is true for the first differential equation for function f1 of psi. There, the role of constant c is played by the following parameter. As before, the wave function is bounded only when the corresponding parameter is equal to some negative integer. Summing up equation for the c and c prime, we arrive at the following equation. Let's denote the integer number in the right hand side by n. Then we have for our kappa parameter the following equation. As a result, we have the famous energy quantization of Coulomb field. Now you are ready to solve some more interesting problems combining the spherical and axial symmetry. So grab the homework and enjoy.